Good evening, everyone. So, welcome to my YouTube channel, Maths Satram. So, today we are going to see fifth lecture on infinite series. Today we'll see the proof of uh, com- today we will see the proof of limit comparison test. Okay? So, let's start today's session now. So, before proving the limit comparison test, it is necessary to see the following result. So, you can say this is proposition. You can say small result, whatever you want to say. You say, okay. Let summation n goes to 1 to infinity a n be a series. Okay. Then summation n goes and and k is belongs to R. K is non-zero real number. Then summation n goes to 1 to infinity. K a n is convergent if and only if this series is convergent. Okay. Solution. So put Sm is equal to summation n goes to 1 to infinity n goes to 1 to m a n and Sm dash is equal to summation n goes to 1 to infinity k times a n. Okay. So actually what we are doing, we are taking partial sum of both the given series. Okay. Then Sm dash is nothing but you can take k common outside and goes to m a n. Okay. So what is this? So what is this actually? This is Sm. This is Sm. This implies Sm dash is equal to k times Sm. Okay. Now first assume that first assumed that this series summation n goes to 1 to infinity a n is convergent. Then limit of m tending to infinity Sm exists. And let's say the limit of m tending to infinity Sm is equal to L. Okay. Now, 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 what is the limit of m tending to infinity? Sm dash. This will be k times limit of m tending to infinity Sm, that is k times L. So this implies limit of m tending to infinity m dash exists and limit of m tending to infinity Sm dash is nothing but k times L. Okay. Okay. Sm, therefore, therefore, the series summation n goes to 1 to infinity k times an is also convergent. Okay. Now, conversely, assume that assume that summation n goes to this series Kan is convergent. Then limit m tending to infinity Sm dash will exist, and let's say limit m tending to infinity Sm dash is equal to L. Okay. Now next, Sm dash is nothing but k times Sm. So this implies Sm is equal to 1 upon k Sm dash as k is non-zero. There, so this implies limit m tending to infinity. So this limit, I am saying this limit, I am saying this limit L dash. Okay. So limit of m is Sm is equal to 1 upon k times limit of m tending to infinity Sm dash, that is L dash upon k. Okay. So this implies limit m tending to infinity Sm exists and limit it is equal to m dash is equal to L dash upon k. So this implies this series An is also convergent. So our result is done. Okay. Now we are writing a corollary. Corollary. Let this series be a series and k is non-zero. K belongs to R. K belongs to K belongs to R. K is non-zero. Okay. Then this series n goes to 1 to infinity. K times An is divergent if and only if this series n goes to 1 to infinity An is divergent. Okay. Proof. First, assume that this series n goes to 1 to infinity, an is divergent. Now, we will prove by contradiction if possible. Suppose that this series summation n goes to 1 to infinity, a times an is convergent. Okay. Then, by proposition, we get that this series summation n goes to 1 to an is also convergent. But which is a contradiction? Which is a contradiction because we have assumed that in first state sentence that series is convergent. Okay, this which is a contradiction. Therefore, this implies summation n goes to 1 to infinity k times an is also okay is also divergent. Okay, is also divergent. Now, conversely, assume that this series k times an is divergent. Okay, divergent. If possible, suppose that this series summation n goes to 1 to infinity, an is convergent, then by position, this series summation n goes to 1 to infinity, k times an is also so if possible supported this series is convergent by proposition is also convergent, which is a contradiction because we have assumed that the series summation n goes to 1 to infinity k times n is divergent. Therefore, this series summation k goes to an is also divergent. Okay, it is also divergent. Now we come to uh, proof of the limit comparison test. What is limit comparison test? Limit comparison test. We recall it again and give its proof. Test. Let summation n goes to 1 to infinity an and summation n goes to infinity bn be two positive term series. Okay. The terms of the both the series are positive. It means an and bn are positive for all n belongs to. Number one, if limit n tending to infinity an upon bn is equal to L, where L is non-zero finite number then both the series converge or diverge together. Okay. Okay. Second one is that if limit n tending to infinity a n upon b n is zero. Okay. Zero. And this series summation n goes to 1 to infinity bn series is convergent, then this series summation n goes to 1 to infinity an is also convergent, but converse need not to be true. Okay, need not to be true. Converge means if uh, converge need not to be true. Okay, okay. So let's see third statement. What was that? If limit n tending to infinity an upon bn is equal to infinity and this series summation n goes to bn is divergent. Okay, then this series summation n goes to 1 to infinity an is also divergent, but converge need not to be true. Okay, now let's see proof. Its proof. Proof. So proof of first part. We will prove first part. Okay. Now limit n tending to infinity an upon bn is L belongs to real number and L is non-zero. Okay. So since an is positive and bn is also positive for all n belongs to n, L is non-zero, we get the limit will be positive. It means L is greater than zero because sequence is positive and it is non-zero. The limit of a positive sequence either it can be zero or it can be positive, but it is not zero, so it has to be positive. Now, now fix epsilon greater than zero such that L minus epsilon is positive. Okay, as L is positive and epsilon is positive, it is obviously implies L plus epsilon will also be positive. Now, limit n tending to infinity an upon bn is equal to L. Then by then then this sequence, then the sequence an upon bn is converging to L. So this implies there exists capital N belongs to N such that an upon bn minus L less than epsilon for all n greater than capital N. Okay. So what is the meaning of this? Is if and only if minus epsilon an upon bn minus L less than epsilon for all n greater than capital N. Now again solving this, what we will get? This is happening L minus epsilon less than an upon bn less than L plus epsilon for all n greater than capital N. Okay. Now, so what is this? What is this? This is L minus epsilon bn less than an L plus epsilon bn for all n capital N. Okay. Okay. Now let's say this is a star equation. Now we saw that. Now we saw that this one. Now we saw this. We show that this series is convergent. Is convergent if and only if this series Bn is convergent. If we can show this, then divergent case will be also settled. We will show this part. This part we will show. Okay. We show this part. Okay. Now first assume that this series summation 1 to an is convergent. Okay. Convergent. Okay. Convergent. Now this is convergent. Convergent. Now, so then this series summation n goes to 1 to infinity 1 upon L minus epsilon an times is also convergent by proposition, because we are taking my k is here 1 upon L minus epsilon. Now from star we have L minus epsilon bn times an. This implies bn, okay, 1 upon L minus epsilon an. Okay. So you see that you can consider this is a new term of this series. 1 upon L minus epsilon an is a new term series. Okay. For all n greater than capital N. Okay. For all n greater than capital N. Okay. And this series summation n goes to 1 to infinity an 1 upon L minus epsilon is convergent. This series convergent. Now, only problem is that we are starting terms from here, but adding a convergent series finite numbers of terms or adding subtracting finite numbers of do not change the convergency of the series. If you have a series, if you add finite numbers of terms, it remains convergent. Okay, if you subtract finite numbers of terms from a convergent series, it remains convergent. Same thing is true for divergent series. If you will add finite numbers of terms to a divergent series, it will remain divergent. If you will add finite numbers of terms to the divergent series, it will remain divergent. Okay, I am starting from here. Okay, so this implies, so how can I write this? Bn is less than 1 upon L minus epsilon An for all n greater than capital M. Okay, and you can start n from this to this. 1 upon L minus epsilon An is convergent. Now we can use here, so by comparison test, okay, comparison test part 1, we get, you can see comparison test. We have done it. Okay, we get this series summation n goes to 1 to n to infinity. Bn is convergent. So this is convergent. We can add finite numbers of terms again. Bn is convergent. So this implies summation n goes to 1 to infinity. Bn is convergent. Okay. Now conversely assume that conversely assume that conversely assume that this series summation n goes to 1 to infinity. Bn is convergent. If this is convergent, this implies this series will also convergent. If I will truncate leaving finite numbers of them, it will be also convergent. Is convergent. Okay, it will converge. Now, so this will implies this series n goes to 1 to infinity. L plus epsilon Bn is convergent. Okay, this is convergent, and An is less than L plus epsilon B times for all n greater than capital N. Now, both from these two. Again, by comparison test part 1, by comparison test part 1, we get this series summation n goes to 1 to 3. An is convergent. Convergent. So this implies this series An is convergent. Okay. Now, similarly, by help of comparison test part 2, we can show that this is divergent, if and only if this is divergent. So first part of the limit comparison test is done. Now we move to second proof of second. Let this series is convergent, be convergent, and limit n tending to infinity an upon bn is equal to 0. Now limit n tending to infinity an upon bn is equal to 0. Okay. Then there exists capital N belongs to natural number such that an upon bn minus 0 less than 1 for all n greater than capital N. So this is if and only an upon bn less than 1 for all. Okay, but an upon bn is non-negative term, so it will be an upon bn. Okay, so this implies so we have an less than bn for all n. Now this series is convergent, bn is convergent, implies this is also convergent, skipping finite of numbers terms, bn is also convergent. Next, an is less than bn for all n greater than capital N, and this series summation n goes to 1 to n t bn is convergent. This here we can from these two conditions we can apply limit comparison test part first by comparison test part first we have we have we have summation n goes to capital N goes to n is convergent. So this implies this series is convergent. Okay. Now converge need not be true. Converge need not to be true. Let's see example. Take an is equal to 1 upon n square. Bn you take 1 upon n. Okay. Limit n tending to infinity. An upon bn is limit n tending to infinity 1 upon n that is 0. Okay. Now this series is convergent. This is 1 upon an is equal to 1 upon n square is convergent because this is convergent as p value is 2 that is greater than 0. If you have auxiliary series p is greater than 1, if p is greater than 1, such series are convergent. So this implies this is convergent. But this series Bn. But this series Bn is equal to summation is divergent. Okay, as n is 1, as p is 1. Okay, now so this part is done. Now we prove third part. Okay, now we prove third part. Now let limit n tending to infinity a n upon b n is equal to infinity, and this series n goes to into infinity, bn is divergent. Is divergent. Now limit n tending to infinity a n upon b n is equal to infinity. So this implies there exists capital N belongs to n such that a n upon b n absolute value will exceed 1. But a n upon b n is positive. So which is if and only because a n upon b n is positive 6 and this will happen. So again, how to write this? How to write this? A n is greater than b n for all. Okay. So we have a n is greater than b n for all and greater than capital N. Okay. Now this series n goes to 1, bn is divergent, implies summation bn is divergent. We have an is greater than bn for all n belongs to n, and this series summation n goes to into infinity, bn is divergent. So by comparison test part 2, we have we have we have this series is divergent. So this implies this series an is divergent. Now converge need not be true. Converge need not to be true. Okay. Converge need not to be true. So let let that an is equal to 1 upon n, okay, and bn is equal to 1 upon n square. So limit n tending to infinity an upon bn, what is this limit n tending to infinity? This is infinity, okay, and this series is convergent. Sorry, this series an is 1 upon is divergent, but this series, you see that this series is divergent. This series is divergent, but summation n goes to 1 to infinity. Bn is equal to summation n goes to 1 to infinity. 1 upon is convergent. So this is convergent. So this series is convergent and this is divergent, and their limit an upon bn is infinity. Okay. So convergence need not be true. So today's class is to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.